The electrical power supply system for a single-engine aircraft consists of a generator or alternator with the control and indication equipment necessary to meet all of the aircraft's electrical power requirements. It will be backed up by a battery. With multi-engine aircraft, 2 or more generators or alternators are installed, and they may operate in parallel. The current supplying and carrying capacity of an aircraft electrical system is determined by the requirements of the power-consuming devices or loads fitted. In this lesson, we will look at the components that make up the electrical power supply system on a single-engine aircraft. Electrical power supply systems may be either of the dipole or unipole type. A dipole or 2-wire system is required where an aircraft is made of a non-conductive material. The current needs a complete circuit to flow, and therefore needs a negative wire to connect the load to the negative side of the generator, as well as a positive or live wire to connect from the distribution point or busbar to the load. The unipole, single pole, or earth return system is the most common type of system on aircraft made of metal. The metal airframe is used as the negative conductor, completing the circuit for the current flow. The negative side of the generator is connected to the airframe. This is known as an earth connection. In electrical diagrams, an earth connection is shown by this symbol. All parts of a circuit with this symbol can be considered to be connected together. The negative side of each load is connected to a suitable point on the airframe near the load. Again, this is known as an earth connection. The current can now flow through a single wire to the load, and the return current will flow through the airframe to the generator earth point and back to the generator. This type of system reduces the amount of wiring required by almost half. This, of course, produces a significant weight reduction. However, it does mean that if any bare positive wire should come into contact with the airframe, there will be a high flow of current through the circuit. This is known as a short circuit, and it can damage the electrical components, as well as producing sufficient heat to pose a fire risk. For a short circuit to occur in a dipole system, both the positive and the negative cables would have to be damaged. A simple aircraft electrical system will consist of a generator, a busbar, loads, and a battery. The busbar is a distribution point to which all of the loads are connected. The generator, battery and loads are all connected in parallel. Parallel connection ensures each load is individually controllable and receives the same voltage. The generator voltage is maintained slightly higher than that of the battery voltage to maintain the battery fully charged. The first component that we will look at in our single-engine system is the generator or alternator. Generators and alternators are normally engine-driven and are used to convert mechanical energy to electrical energy. As you have already seen, a generator produces direct current or DC using a rotating armature, stationary field and a commutator. whereas an alternator produces alternating current, or AC, using a rotating field and a stationary armature. If it is required to convert the AC output of an alternator to DC, a diode rectifier is used. This is usually fitted in the end frame of the alternator. Most modern light aircraft have a direct current system, which is powered by an alternator with diode rectifiers. The diode rectifiers in the alternator end frame are solid-state devices, which convert AC to DC and permit the current to flow out from the alternator, but not into it from the battery. They have a very low resistance in the direction of the arrowhead and a very high resistance in the other direction. The voltage regulator maintains the output voltage of the generator or alternator at a constant value, irrespective of the engine RPM or electrical loads. As you have already seen, this is achieved by controlling the current flow in the field coils of the generator or alternator. The voltage regulator controls the generator output to maintain 14 volts for a system with a 12-volt battery and 28 volts for a system with a 24-volt battery. An over-voltage protection unit is fitted to protect against the output voltage of the generator rising dangerously high and causing damage to aircraft circuits due to overheating. It is primarily protecting against voltage regulator failure. The over-voltage protection circuit will automatically disconnect the field circuit if the voltage rises to approximately 20% above the normal generator output voltage, thereby reducing the generator output to zero and safeguarding the system. The generator or alternator master switch is a pilot-operated switch. It enables the pilot to electrically isolate the generator or alternator. Opening the master switch breaks the field circuit, causing the generator output to fall to its residual level, which is virtually zero. The generator cutout, or reverse current relay, permits the generator voltage to build up to a preset figure before its contacts close and put the generator online. The term online means that the generator or alternator has been switched into the electrical system and is actually supplying power to the system. The reverse current function causes the contacts to open to prevent the battery feeding current back into the generator when the generator voltage is below that of the battery voltage. The cutout may be an integral part of the voltage regulator, or it may be a separate unit. The reverse current function is not used in an alternator system, as the diode rectifiers provide reverse current protection. We will now take a closer look at the generator cutout to see how it works. It operates in very much the same manner as the standard electrical relays that you have seen previously. It consists of a soft iron core and an armature with a pair of contacts connected to it. The contacts are sprung to the open position and will close when the armature is magnetically attracted to the core. The difference between the reverse current relay and a standard relay is that the core has two sets of windings or coils wrapped around it. The voltage or shunt coil has many turns of thin wire and is connected in parallel with the generator output. The series or current coil has a few turns of thick wire and is connected in series with the generator output. The generator output current passes through this coil. Here, we can see what the system would look like with the generator not turning and not producing an output. There will be no current flowing in either coil, so there will be no magnetic attraction and the contacts will be open, isolating the generator from the busbar. As the generator starts to rotate and builds up voltage, current will begin to flow in the voltage coil. When the voltage has built up to a predetermined value, which will be greater than the normal battery voltage, there will be sufficient current flowing through the voltage coil to produce a magnetic field strong enough to overcome the spring and close the contacts, connecting the generator output to the busbar or bringing the generator online. The generator output current will now flow through the current coil. This current flow is in the same direction as the current through the voltage coil, so it increases the strength of the magnetic field and helps to keep the contacts closed against the spring. If the output voltage of the generator falls below the battery voltage, then current will begin to flow from the battery toward the generator. If this was allowed to continue, the generator would almost certainly be damaged, and the battery would become discharged very quickly. The falling voltage of the generator will cause the strength of the magnetic field produced by the voltage coil to reduce, and as the current flow through the current coil will be reversed, then the magnetic field produced by it will also be reversed. This magnetic field will now be opposing the field produced by the voltage coil, and there will be insufficient magnetic force to hold the contacts closed, and they will spring open, disconnecting the generator from the busbar and preventing further reverse current into the generator. Some electrical loads require an alternating current or AC supply. On aircraft with a DC electrical system, the AC is produced by the use of an inverter or inverters. Inverters can be either static or rotary. Modern inverters are of the static type and use solid-state electronic components to convert DC to constant frequency AC. The static inverter can accept a range of DC input voltages and still produce a steady AC output. The most common AC output is 115 volts AC at 400 Hz frequency. The frequency of AC electrical supplies is fully explained in the AC lessons. Rotary inverters are older devices designed before the advent of solid-state electronics. They convert DC to AC by using a constant-speed DC motor to drive an alternator, thereby producing constant frequency AC. A busbar, sometimes abbreviated to bus, is the collection and distribution point for a generator or alternator power supply. Busbars are usually situated in junction boxes or distribution panels located at central points within the aircraft, and they provide a convenient means for connecting power supplies to the various consumer circuits. In its simplest form, A bus bar can take the form of a strip of interlinked terminals. While in more complex systems, main bus bars are thick metal, usually copper, strips or rods, to which input and output supply connections can be made. If a cable connecting a load to the bus bar should become disconnected, the load is said to have become open-circuited and will no longer operate. The battery will normally be lead-acid or alkaline, and depending on the system, it will have a voltage of either 12 or 24 volts. It can be used to start the engines or to supply electrical power in the event of generator or alternator failure. The battery switch is a pilot-operated switch. It allows the pilot to connect the battery to or to disconnect the battery from the bus bar. That is the end of the lesson. Here is a summary of the main points. A dipole or two-wire electrical system is required, where an aircraft is made of a non-conductive material. In a unipole, single pole or earth return system, the metal airframe is used as the negative conductor, completing the circuit for the current flow. This type of system produces a significant weight reduction. However, there is an increased short-circuit risk. The voltage regulator maintains the output voltage of the generator or alternator at a constant value, irrespective of the engine RPM or electrical loads. The overvoltage protection unit protects against the output voltage of the generator rising dangerously high. It is primarily protecting against voltage regulator failure. Opening the generator or alternator master switch breaks the field circuit, causing the generator output to fall to its residual value, which is virtually zero. The generator cutout or reverse current relay permits the generator voltage to build up to a preset figure before putting the generator online. The reverse current function prevents the battery feeding current back into the generator when the generator voltage is below that of the battery voltage. In an alternator system, the diode rectifiers provide reverse current protection. Some electrical loads require an alternating current. On aircraft with a DC electrical system, the AC is produced by the use of an inverter or inverters. Inverters can be either static or rotary. Static inverters use solid-state electronic components to convert DC to constant frequency AC. Rotary inverters convert DC to AC by using a constant speed DC motor to drive an alternator. The bus bars are the collection and distribution points for a generator or alternator power supply. The battery switch allows the pilot to connect the battery to or to disconnect the battery from the bus bar.